we continue. The Bode plot of the lead controllers. Lead controller is given by S plus A, S plus B, and its location of the 0 is minus A and minus B. So that location is like this, okay? And so for this one, we draw it for J omega, S equal to J omega here. Let me rearrange this one a little bit. So GC of S will be equal to, usually for drawing these kind of functions, for example, G say equal to S plus 2 and S plus 1. And for our drawing, the good exercise is you better to have the constant term scale to 1. Okay, so here you have basically like this, because later on once we introducing the S equal to J omega here, so for example here it's equal to J omega, so sound is a 2. So that means looking for these terms here, the omega, if you keep this good exercise, then basically for these terms, the omega equal to 2 is corner frequencies. Okay, so that will simplify the drawing, the minor drawing on here. Of course, this is not required, but it's a good exercise. You scale the constant term to 1. Okay. So for this case, let me scale is 1 plus S over A and 1 plus S over V. Okay. So based upon this, then we introduce S equal to J omega. So that is 1 plus J omega over A, 1 plus J omega over B. Then based upon this one, I'm going to draw the plots here. And right now for this case, the value is A, AB are both positive and N less than B. So basically this one is a combination of this is the linear function, this is the first order function, these are first order functions here. Then we can try is this. Okay, so this is G, J omega, and in dB. Okay. And this one is log omega. And this one is the angle, GC, J omega, and in degrees. Okay. Usually this one should be, okay, whatever. So based upon this, and we can say when we label A and B. A is smaller than B, so let me just arbitrarily, okay, just arbitrarily label the AB here. Okay, so omega equal to A and omega equal to B here. Okay. Okay, so now for this one, we simply do the calculations. Basically, here we like to sketch is to label a few key points, the value of the magnitude and phase angle at a few key points, and at least, and to help us. So when omega is very, very small, then we'll look at this one. When omega is very small, basically let me do the calculation here. The magnitude, and this is the phase angle. Okay, and when omega is very, very small, then we look at this one, then this one become 0, 0. So basically this is equal to 1. Okay, and the magnitude equal to 1 basically is become the decimal that is 0. Have anyone found the mistake
K.
Yeah, right? So here I scale, basically here I should be A because I need to make the whole thing consistent, right? Good? Okay, so Scott, you're good. So that's the reason why I've been seeing you keep smiling for a few minutes. I don't know what happened to you. That is the reason. You know what I'm saying? Okay, so that's the mistake here. So this one, and here is a constant, okay? So when K equal, this one small, basically this value equal to A over B. So that means when omega is very small, then let me say this is my drawing point, that is the log, and A over B times 20. So let me set up this value is here. Okay, so at small, so basically this is the point we have, okay? And for angles, again, for angles, this one basically is 0 degrees. Okay, and again, when the omega is very small, we can calculate. So let me do this one. So this angle will be equal to the arctangents omega over A minus arctangents omega over B. Okay, so that is the calculation for angle, keep that in mind. And then we move on to say omega is very big. Okay, and so under these situations, if omega is big, then omega is big, then how much is that one? When omega is big, then its magnitude is equal to the here I do the calculation. The magnitude is approximate omega over A and omega over B, and this is the over B. Okay, when omega is big, we can approximate by this, and then we cancel this one. Basically, this is equal to 1. Okay, so that means when this one approaching to is here. So when doing the large omega, that is value is here. That point, this value corresponding to here is 0. And because for this case, A is less than B, so basically this magnitude is a -1. Okay, so here let me just draw the asymptotes here. So that's kind of asymptotes, and then we can work on the details. And now we work on is at the quarter frequencies. And for this example, we have two features called the frequency. One is when omega equal to A here, okay? So when omega equal to A, and then basically the magnitude is equal to assuming the AB is becomes the difference, the AB difference is say at least the order of the magnitude apart. Okay, so assuming in that way, so basically for this case, we might assume when at this frequency here, then GC will be approximate, will be equal to say, because at omega A is smaller than B, so this one is about say 0. Okay, so for example, omega equal to A compared to B, assuming that is small, so basically here numerator equal to 1, and this one basically equal to J. Okay, so making that assumptions, the magnitude is basically equal to 2. So the square 2, and if we take the decibel of the square 2, again I always forgot the AB here. Let me redo this one. So this is A over B. Okay, so that is A over B. Okay. So here we take the log of the A over B, and basically multiply with 20. Basically it's 20 log and square 2 plus 20 log A over B. So this one is what we have a value here, and this value is equal to -3 dB. 3 dB. So basically, at the corner frequencies, the magnitude of the GC basically is 3 dB above this level here. So let me label that point. Okay, so the distance at the corner frequencies, again, that is 3 dB. And I told you the 3 dB is a magic number appear in the frequency domain analysis. Okay, so, and 3 dB is based on this calculation. Whenever you have the magnitude equal to square 2, then corresponding in decibel, that corresponding is 3 dB there. At the corner frequencies, the difference between the asymptotes and the exact value is 3 dB. Okay, so in the same way here, for B here, and again for B here is our asymptotes, and again this one is lower than 3 dB here. Okay, so basically here, if you like to draw it, you can have the drawing like this, approximate. Okay, so come here, you can come to this one, and another good exercise is you can look at like this. Another good exercise you can visualize like this. If you remember our exercise of single term here, so earlier we have the exercise of drawing the G S equal to say 1 plus S over A. Okay, we have drawn this one G J omega. If you have your notes ready, you can look at that one for log and omega, and for G, we have this drawing is this. We simply select A here, and when omega is small, basically this data is 0 here. When omega is big, and basically, okay, let me write it down here. 1 plus J omega over A. Okay. Again, we have done this before. And so for this case, G, we have a calculation of omega is small, basically that is equal to 1. And when omega is very big, greater than 1. Okay. So this one equal to basically is determined by omega over A, right? So that means 20 of log G. This one equal to 0. Basically, this one is the governed by 20 log omega over A, and that one basically equal to 20 log omega and minus 20 log A, something like this one. Basically, the magnitude for this case is governed by a slope. So that means the slope equal to 20 decibel per decade. So that is the asymptotes, and then for here we can precisely draw it again at the corner frequency here, that is 3 dB. Very good? Okay, so here is the asymptote. asymptote, basically here you draw a straight line, and here they have the two straight lines, the asymptotes intersecting at the corner frequencies. At the lower end, that is the zero slope, and here that has the slope 20. And in the similar way for GS equal to 1 and S over B here. So for the similar ways, and G J omega equal to 1 plus J omega over B. So for this case, the same thing we've seen before. This is a log omega, and this is G in dB. For this case, let me say the B is here. The asymptote is this one. Okay, and for this case, because this term is in the denominators, if you do the simple calculation, actually you can find the asymptote is with a negative slope and in the decibel minus 20 decibel per decade. Have we seen this before? I believe so, right? Okay, and so that means the curve will be something like this. Again, at the decibel, at the corner frequency here, the difference is 3 dB. Be good? Have we seen this before? I believe so. Yeah, I think we have done this before. And if you look up the lectures on the first order system, I think back to 2 lectures hours ago, and I should have a video available on YouTube. Okay, so for this case, we can compose the 2 things together. So here for this case, our example here, A is less than B. So here we choose A is here. And at the lower frequencies, the information is governed by these features. So you can have the asymptotes being drawn like this, okay? And the same thing for the higher frequencies, and that is the behavior is governed by this case. So you can have the asymptotes being drawn like this. So this is 20, and the slope is minus 20. Okay, so basically the unit is the decibel per decade. Okay, so here you compose. Okay, compose, that means the combination of the 2 things is the log. So that means here you try to add the curve together. So here let me put the frequencies A and B here. Okay, so right now we simply added up the 2 curves here. So this one, basically this one, one more. Let me release a more space above. So let me rewrite here. So GC J omega equal to A over B, and 1 plus J omega over A, 1 plus J omega over B. Okay, so one more curve here. And so here we have 3 terms. First term, second term, and the third term. So let me label this the first term, this is the second term, this is the third term. For the second term, that is drawing at here. For the third term, that is drawing at here. And then for the first term, I want to draw it on the top. And for the first term, basically that simply is contributions. I would say here is the second terms. Okay, so this is the first term. For the first term, basically is log 20 A over B. So basically here, let me label it. So that is a constant all the way through here. So the magnitude is 20 log A over B. Okay. For the second term, this is starting from 0. For the second term, for the third term, that is 0 here. And right now, we simply do the superposition of the three curves. And again, let me do the asymptotes first. For asymptotes, then we added up the two lines together. Basically, here at the lower frequency, less than A, the asymptotes added up is like this. Very good? In the middle range, this is a 20 above, this is the 0. So if you add the point by point, basically in the second range, that is like this. The slope equal to 20. Good? For the third one, right now here you can see this one keep going as a 20. But right now in the third range, this is above 20, this is minus 20. They added up together, become net 0. So for the third one, starting from here and then they become 0. Very good? Okay, so that is the asymptotes for the compositions of the three things. And now we simply put things together. And now at here, this point is above by 3 dB. And the real value for this one is 3 dB below. So here you can add it up the point by point in terms of the value. So here is the value here. You pretty much approximate. And you can say here for approximation, this is about 3 dB. But due to the composition, that might reduce to 2.9 something. We don't know, but we can calculate if necessary. But here for approximation, you can just say 3 dB, that's okay. Okay, and now for this case, this is about 3 dB, and that point to come to passing through there. Okay, so right now you're simply connecting the wave, so basically that is passing through something like this one. Okay, intersection should be right away in the middle there. You good? Yes or no? Yes. Okay. So with this one, then this is a magnitude. And if you want to continue on this one, again, here you can continue to phase. And basically for this site, basically we just, for each corner frequency, we keep continuing. So let me do complete this site first. At least for this site, the magnitude we have completed. You can see for this calculation, we simply, every time for every single scenario, we just do the calculation based upon the magnitude. Okay, and for this case, we decompose whatever the single term, we decompose into the generic terms we have done before. Then we borrow the concept and then we do the compose. Two methods, up to you. Okay, and now let me finish the phase for this one. Okay, so now for this one, let me finish the phase. So for the phase here, and so when omega equal to A, the phase here is arctangent, and omega equal to A, and that is A divided by A, and minus the arctangent and A divided by B. Okay, so basically this is arctangent 1, and arctangent 1 that is 45 degrees and minus something. A is smaller than B, so I would say this is certain number, smaller number, I would keep writing. Okay. So when omega equal to A, so that means this is 45 degrees, and so let me put into, so say this is 0 degrees. How about this? Yeah, whatever. Okay, so this is 0 degrees, and then 45 degrees, and then 90 degrees. Okay. So for this case, that would be some value less than, so that is the point here. Okay, and depends on the ratio of the AB. And when omega is very small, that is here. Okay, so that is down here. When this is greater than 1, then for this case, so this one is arctangent. Omega is large, so very large. So I would say infinity minus arctangent infinity here. And this one basically is almost 90 degrees minus 90 degrees is 0 degrees. Okay. So here I would say in very large. So that one basically come back to the 0 degrees there. Okay. So now we continue at a quarter frequency omega equal to b. So that is arctangent, and b over a minus arctangent 45 degrees. Okay, so basically this is b larger than a, so that is arctangent, for example, 2 or 10. So that value is larger than 45 degrees. Okay. So basically this will be the positive numbers here. Okay, so that means here depends on the value, we can put something just arbitrary. Okay, something there. Okay. So now for this case, we can also exercise the phase angles here. So again, from our earlier exercise, we have a phase angle. Let me draw the phase angle on this side here. So now again, for the earlier exercise, we have a phase angle for so this is a phase angle for this system here. Okay, for this system here. And for this system, and say when omega is very small, then the phase angle basically equal to 0 degrees. Okay, and so the phase angle basically is the arctangent of the real part, and the imaginary part divided by real part is given by this one. So when omega is very small, basically this is 0 degrees. When omega becomes very big, then basically that is arctangent of infinity approaching to 90 degrees. Okay, and then at the quarter frequencies here, when omega equal to a, and so when omega equal to a, basically that is arctangent 1, so that is 45 degrees. So at the corner frequencies, we have this one. So the approximation for this is something like this. Okay, so now for this case, let me redraw this one here. So now again, we have the 3 terms, and here is the angle of the first term, and that is a constant. Basically, that is 0. Degrees. So that is in degrees. For the second term, that is the second term, and again in degrees. And the second term is basically like this one, so that's what we have done. So here is the A here, and 90 degrees. Okay, so that's the 45 degrees. So the asymptotes is like this. Okay, and basically here is 45 and 0. Okay, and now for the third term. For the third term, that is B here, and for this case, we can calculate. So for G equal to, for this term, that is the degrees of the angle of the numerator minus the angle of the denominators, and so that is arctangent omega over B. So again, for this case, when omega is approaching to a large, okay, when it's large, then G approaching to minus 90 degrees. When omega I is small, then G basically equal to 0 degrees. When omega I equal to B, then for this case, the G equal to minus 45 degrees. So from here, again, we can have this kind of thing, 0 degrees and 45 minus 90 degrees. So here the asymptote is something like this. Okay, so at point, so here is 0, at point B here is minus 45, so something like this. Okay, good. Now we can compose. So now we compose the whole things. So that means adding the three numbers together, basically that will give us the GC. And so from there, that will be something like omega, and then that is the 0 degrees here. Okay, so A, B. So at the lower frequency range, that is almost 0, so we know that will be starting from 0. And A here, at the corner frequency A, that is about, this is the 45 degrees and plus 0 degree, and this one will be a little bit negative. So I would say here, let me label that one. So this is 45, and here is 90. Okay. So at A here, that will be a little bit smaller than 45 degrees. Okay. And then here again, this is minus 45 plus a little bit. This is a minus 45 and plus say 89 or 80 something. So that is less than 45. So that is something like here. Okay. So in between, basically this is larger, say 70, and this is very small, say minus 20. So basically here you can basically in between something like this one, approximate, and then going back to 0. You good? And have the manual, you learn the skills by manual drawing that will help you to quickly analyze the something, and later on we're going to use it. Okay. So so for these sections we've done this.